All right, welcome back. This is section 13.2, day 1. We are looking at derivatives of vector-valued functions. And just like when you learned about derivatives in single variable calc, we're going to start with the definition of the derivative of a vector-valued function. Let's do a real quick recap, a little throwback to Calc 1. If you had the definition of a derivative in Calc 1, let's just say you have some curve. Here's x, and here's y equals f of x. And let's take 2 points on that curve. Let's let this point be the point x with height f of x, right? And we're going to shift to the right h units. And so this new x value would be x plus h, and therefore this height would be f of x plus h. So then I'm going to connect the secant line between those 2 points. And what you learned last year was that the slope of that secant line would have been the average rate of change of that function f, and it would have been represented by rise over run, y2 minus y1 over x2 minus x1. So f of x plus h minus f of x over x plus h minus x would be h. And then the idea behind the derivative is that we're trying to find the slope of the tangent line. So we want it to only pass through one point, which in this case, let's let that be x. As we let that distance h approach 0, so as the distance between x and x plus h gets smaller and smaller, eventually we end up getting a tangent line that only passes through one point, right? Because now we've shrunk that distance as it's approaching 0. So the slope of that tangent line ends up being the derivative at x. So the slope of the tangent line is the limit as h, the distance between those 2 points, approaches 0 of that difference quotient, f of x plus h minus f of x over h. Okay, so that's for a function. So what about for a vector-valued function? Well, it's defined in a pretty similar way. Remember from our last section, let's let a space curve be defined by r of t. Okay, so we have some curve in space, r of t. Think of it as like a position function. The derivative, r prime, so r prime of t, is defined pretty much the same way that we would define this for a scalar function, f of t. It's the limit as h approaches 0 of r of t plus h minus r of t over h. Looks like a pretty similar format. Geometrically, what are we looking at now, though, right? We're not just looking at points, we're looking at vectors. So we're going to connect a vector from the origin out to our initial point P. So we'll call that vector just r of t. We're going to shift h units, and so then we're going to connect out to a new point. We'll call it Q. So this would be after maybe t is time, after some shift in time by h units. This is our new position vector, r of t plus h. And so the difference between those two vectors, if you use the tip-to-tail method using vector addition, I'll draw this one in blue, this vector pq ends up being the difference between r of t plus h and r of t. And you can check that with vector addition. Well, what about this division by h? What's that going to do? All that's going to do is it's going to rescale that blue vector and make it longer. Because we're trying to make the distance between r of t plus h and r of t smaller, we're trying to make that distance between the 2 points smaller and smaller. Think of this as the reciprocal, right? This thing right here, another way of writing that is 1 over h times that difference. So it's going to take that vector in blue, pq, and it's going to scale it. It's going to give me a scalar multiple of that difference vector. So it's just taking the vector pq, it's taking this vector r of t plus h minus r of t, and it's producing a parallel vector, right? It's scaling it in size. So what happens as I let h approach 0? Well, as I let h approach 0, the 2 points are going to converge closer and closer together. And in the end, what we're going to get is a vector that doesn't pass through 2 points, okay, but it passes through 1 point, which I'll outline in pink. And so this vector that only passes through P, that is my tangent vector. Okay? And that indicates that's the derivative. Okay? So kind of to sum up here, if points P and Q have positions r of t and r of t plus h, then PQ represents the vector r of t plus h minus r of t, which we can regard as a secant vector since it passes through 2 points, P and Q. Okay? Scaling it by 1 over h. So when we divide that difference by h, we're going to produce a vector that has the same direction as PQ. Here's my new vector. And as we let h approach 0, this vector appears to lie on the tangent line. So if this was the entire tangent line, then that pink vector could indicate the direction of that tangent line, right? And that tangent vector we can define by r prime of t. That vector is called the tangent vector. It indicates the direction that the curve is moving. Okay? So it points in the direction of increasing parameter. As t increases, that indicates the direction of that curve. Okay? And the tangent line to that curve, C, at that point P, is defined to be the line that goes through P and is parallel to that tangent vector r prime of t. So in other words, r prime of t would end up being the direction vector of your tangent line. Remember how we've been writing equations of lines in parametric form? We needed a point on that line and we needed a direction vector. Well, when we write the equation of the tangent line, our direction vector will be r prime. It'll be that tangent vector, that derivative vector. We'll do some problems like that in a little bit. Okay, so just a little bit of background. Much like we defined limits for vector valued functions, we can define the derivative of a vector valued function. Let's say that our position function r of t is given by f of t, g of t, h of t, okay, in 3 space, where f, g, and h are all differentiable functions. Then the tangent vector r of t is defined to be just the derivative of the 3 component functions. So my 3 component functions were f, g, and h. The tangent vector is going to be the derivative of f, the derivative of g, and the derivative of h. That will make up its 3 components. You can write this in component form. You can also write it using the standard basis vectors I, j, and k. Okay, so again, here's my picture in blue. This would be, if this was my point I was passing through, this would be my original position vector r of t. I'm going to sketch these in different colors here. In red, the picture is labeling it v of t. You can probably take a guess that means velocity. When we start reviewing position, velocity, and acceleration in section 13.4, what we'll see is that the tangent vector really is just the velocity vector. So for now, let's just call this red vector r prime of t, but eventually, in the context of PVA, it'll be the velocity vector. Well, it gives quite a bit of information. It indicates the direction that the curve is moving, right? But what we're going to want to do a lot of times in this class is we're not going to want to over quantify or give too much magnitude to these vectors. We want the direction to be its own component. And so the downside of having that tangent vector is that it doesn't always have a length of 1, right? So we like to have unit vectors in this class. So how do we turn the tangent vector into a unit vector? It's going to indicate the same direction, but it's going to have a length of 1. And so we have what's called the unit tangent vector. We're going to call it t. It's going to be probably the most popular vector that we talk about this entire year. And to create that unit tangent vector, remember what that means? That's the length of that vector. Has to be 1, right? Unit vector means length is 1. Well, to create a unit vector, we saw this a couple sections ago. We take our vector and we divide by the magnitude of that vector. So my tangent vector is r prime of t. To make it a unit vector, I'm going to divide by the magnitude of r prime of t, that vector norm. And that creates what's called the unit tangent vector. In my picture, I'm going to outline that in pink. That would be this little vector right here. It moves in the same direction as r prime, but it has a length of 1. We're going to use it a lot. Higher order derivatives are defined in the exact same way as the first derivative. So if I wanted to calculate r double prime, all I would do is I would take 2 derivatives of each of my component functions, f double prime, g double prime, h double prime. If I wanted to take the 4th derivative, I would take the fourth derivative of f, the fourth derivative of g, and the fourth derivative of h. So they're defined in exactly the same way. Okay. Let's try an example. Find the derivative of r of t equals 1 over ti plus e to the 2tj minus 2 cosine of pi t times k. So here's my f of t function, here's my g of t function, and here's my h of t function. Okay. And so my derivative of that vector valued function is just going to be the derivative of each of the component functions. So I like to compute them separately and make my vector when I'm done. The derivative of f is given as 1 over t. Let's think of that as t to the negative first. Then my derivative would be negative 1 t to the negative second, or negative 1 over t squared using the power rule. G prime of t, g of t is e to the 2t. Using the chain rule, the derivative would be e to the 2t times the derivative of 2t, which is 2. So 2e to the 2t. And h prime of t, the derivative of negative 2 cosine of pi t, negative 2, lead coefficient, stays put. The derivative of cosine would be negative sine, so times negative sine of pi t times the chain rule times pi. Okay. And so I end up with 2 pi sine of pi t. And so these are going to make the individual components of my derivative vector, of my tangent vector. So r prime of t is going to be negative 1 over t squared, comma 2e to the 2t, comma 2 pi sine of pi t. And you could also express this using the standard basis vectors as well if you want. So I'll put or negative 1 over t squared I plus 2e to the 2t j plus, running out of space, let me shift, 2 pi sine of pi t times k. So your choice. I'm not picky with that. You could do either of these. Okay, now again, that's not a unit vector. So how do I make it a unit vector? We want to find in part B the unit tangent vector at the point t equals 1. So notationally, what we're trying to find is capital T vector of 1. Now, there's a couple ways you could do this. You could find a general expression first for capital T and then plug in 1 to your results. I'm going to just give you a heads up in this example. That's going to get very algebraically complicated because the vector norm of the vector we just found is going to be a square root of a very messy bunch of components. But it would work. You could do it that way. You're just going to have a very messy expression for capital T of t. Since they did not ask for a general expression for the unit tangent vector, my advice would be this. Let's just crank out what this would be by plugging in 1 immediately. If capital T is equal to r prime of t over the magnitude of r prime of t, there's our expression, then capital T at 1 would just be r prime of 1 over the magnitude of r prime of 1. And we already have an expression for r prime, and we can very easily plug 1 into it. So step 1, I'm going to calculate the numerator. R prime of 1, using my expression from part A, would be negative 1, 2e to the second. So I'm just plugging 1 in for t in my expression from part A. And 2 pi times the sine of pi would be 0. Second step, the denominator, I need the magnitude, the vector norm of r prime of 1. So this would be the square root of the sums of squares of those components of r prime of 1. So negative 1 squared plus 2e squared plus 0 squared. So we get the square root of 1 plus 4e to the 4th. Okay. And so now go back to our expression. So this would just be, and you can factor out the 1 over the square root of 4e to the 4th if you'd like. That's fine. Okay. Times our vector negative 1, 2e squared, 0. Okay. And you can also distribute that coefficient through if you'd like and include it with each component. That's up to you. Okay. But you can check. If you take the magnitude of this vector, you'll get 1. That'll be a unit vector. So that produces t capital T of 1. Okay. If you're interested in the decimal version of this, I'm more of a fan of the exact answers on a quiz or test. I'd probably expect you to do this in exact form, but the decimal versions end up being about negative 0.068, 0.998, 0. Okay. Okay. Let's do a sketch. Next one. For the curve, r of t equals rad ti, 2 minus tj, find r prime of t. Then we want to sketch the original position vector r of 1 and the tangent vector r prime of 1. So this will be a good example to give you a visual of the original position vector and the tangent vector to show you that it moves in the direction of the curve. So let's sketch the original curve first. I think that would be a good first step. Okay? So if I do the original curve, so here's my values of t, here's my values of x and y. This is going to be sketching the original curve r of t. Okay. So I'm just going to pick a couple points like 0, 1, and 2. And I'm going to scale my graph. You'll see for size, we're going to want to make this just a little bit bigger. So I'm going to scale every 2 squares will be 1 unit in each direction. If I plug 0 in, I end up getting 0, 2. So my first ordered pair is going to be up here at 0, 2. When t equals 1, I end up getting 2. Square root of 1 would be 1. And 2 minus 1 would be 1. So I'm at 1, 1. And when t equals 2, I get the square root of 2, comma 2 minus 2 would be 0. So rad 2, it's about 1.4-ish. So we're going to end up with our last point's going to be about here. Okay. And I guess how far do we go? Do we go beyond? Do we need to go past the point t equals 2? Well, let's see. We're trying to find r of 1 and r prime of 1. So it looks like we're good. Just going to make this as accurate as I can here. Okay, so there's our curve. I'm going to indicate the direction of the curve, right? It moves in the direction of increasing parameter. Okay, so there's my curve. Okay, we want to find r of 1 and sketch that. So r of 1, okay, in component form, this would be rad t 2 minus t. So that would imply that r of 1 is square root of 1 would be 1. 2 minus 1 would be 1. So from the origin, I'll do this in pink. I'm going to go from the origin. I'm going to go 1 unit out to the right and 1 unit up. So it touches that first dot, that first point. Okay, so that vector there in pink represents, that's r of 1. Okay, so that's my position vector. And now I want to know what's my tangent vector going to look like. So it should point in like a southeast direction. Let's see what that ends up being. So we need the derivative. So this is really t to the 1/2. So r prime of t is going to be the derivative of rad t. So 1/2 t to the negative 1/2, or 1/2 square root of t. And the derivative of 2 minus t would just be negative 1. We want the tangent vector at the point 1, t equals 1, which is at the point 1, 1, which is this point right here that I'm highlighting in yellow. And so plugging in 1, we end up getting 1/2 negative 1. And remember, these vectors don't have to start at the origin. They can start at whatever point you want. So we're going to start from that point highlighted in yellow. We're starting at the point 1, 1. We're going to go a 1/2 unit to the right, which remember is going to correspond to 1 square based on how I scaled. So I'm going to go 1 square to the right, and then I'm going down 1 unit since my y component is negative 1. So I'm going to end up at the point 1.5 comma 0. And so if I sketch this, you'll see half a unit to the right. Maybe I'll do a different color. Let's do this rainbow color here. Yeah, that's kind of hard to see. Let me pick something. There's so many different colors I can pick with this program. There we go. So you can see it's tangent to the blue curve. and it moves in the direction of that curve. So that would be my tangent vector. You can see kind of over off to the side here. Here's my point, and our vector is kind of giving you a zoomed in version, is pointing off. Okay, it's pointing off in the direction of that curve. Okay, so that vector right there is r prime of 1. Okay. And there's our expression for it. All right, next one. Find parametric equations for the tangent line to the helix, a friend that we met in the last section. Given with parametric equations, x equals 2 cosine t, y equals sine of t, and z equals t. So it's going to be one of our spiral shapes that ends up spiraling in the z direction according to that linear function z equals t. And so here's kind of a little visual just to show you what we're going to find. Here's the point that we're interested in. We want to find the equation of the tangent line at the point 0, 1 pi over 2. So if you look at the picture, it's going to be this point right here in pink. And we're going to want to find the equation of this tangent line that the picture has sketched in red. So what are we going to need? Think back to the basics. To write the equation of a tangent line, or any line, we need to have two things. We need to have a point on the line. Check, we have that. The point on the line is 0, 1 pi over 2. And we need to have a direction vector that indicates the direction of that line. And on the first page of the notes for this section, when we were looking at the visual, we said that our direction vector for the tangent line is going to be the tangent vector. So the point we're going to use in this problem is 0, 1 pi over 2. And our direction vector is going to be r prime of, we just have to figure out what value of t to use. So if I look at my expressions, my parametric expressions, I need to figure out what value of t produces the point 0, 1 pi over 2. Using a little bit of trig and knowing some of my famous angles from the unit circle, I know that for x to equal 0, cosine would have to be, or t would have to be pi over 2. And for the y component, sine of pi over 2 is 1. And for the z component, there's my pi over 2. So I am looking at the point when t equals pi over 2. Oftentimes they won't tell you the value of t. You have to find that. So then my direction vector, I'm going to need the tangent vector at the point pi over 2. So our direction vector is going to be r prime of pi over 2. Okay, so first thing, I'm just going to write my position vector. So 2 cosine t, sine t, t. Second thing, I need r prime. I need my tangent vector. My tangent vector is going to be the derivative of my position vector. So I'll take derivatives component by component. Negative 2 sine t, cosine t, 1. And I'm interested at the point when t equals pi over 2. So step 3, I'm going to plug in pi over 2. So I end up getting negative 2 times the sine of pi over 2. Negative 2 times 1 would be negative 2. Cosine of pi over 2 would be 0. And the third component is a constant 1. Okay. This, negative 2, 0, 1, that's my tangent vector. That's going to be describing the direction of that tangent line. You do not need to make it a unit tangent vector in this case, because whether you use, I'm just going to sketch it in the picture here so you can see it. Here's my tangent line. Let's just say this blue vector represents r prime of pi over 2. Maybe it has a length of 1, maybe it doesn't. It doesn't actually. Well, if I scale it down in size and only use t of pi over 2, notice it still indicates the same tangent line. It's still pointing in the exact same direction. It's just a scalar multiple of r prime. So you can choose to use capital T, but it's more work. So I'm not going to use the unit tangent vector. I'm just going to use the tangent vector since it does describe the direction of that line. Okay. So putting it all together, my parametric equations, did they ask parametrically? They asked for parametric. Yep. So my parametric equations for that tangent line, x is going to be the point for x was 0. So 0 minus 2t. Y is 1 plus 0t. and z passed through the point pi over 2, and the z component of r prime was 1, so plus 1t. I'm going to simplify these. So I end up with x equals negative 2t, y equals 1, and z equals pi over 2 plus t. That would be an expression, parametric expression, for this tangent line here in yellow, okay, to that point on the curve. Now, what if we wanted any general point t naught instead of just the point when t equals pi over 2? We can do that. The general expression is going to pass through the point. So we need a point and a direction vector still. The point is just going to be the point produced. This is going to be a vector. Let me erase here. This is going to be the point when t equals t naught for r prime. So if you plug that in, what do we get? We get 2 cosine of t naught, sine of t naught, t naught. So just plugging that in here. And then the direction vector, I'm just going to plug in everywhere I see t, I'm going to replace it with t naught. So my direction vector would be negative 2 sine of t naught, cosine of t naught, 1. So my parametric equations would be 2 cosine of t naught minus 2 sine of t naught times t. Y would be, let's see, y was 1. So 1 plus t times the cosine of t naught. Okay, so t is still a varying parameter. T naught is a fixed value, just to clarify. This t naught is a fixed value. T is still a varying parameter. And then z, if I can fit it here, z is pi over 2. I'm sorry, z is equal to t. So t naught. And our direction was 1. So still just adding t times 1 for t. Okay? So that would be a general expression for the tangent line at any point, t naught. Okay, next one. We have two curves given parametrically by r1 of t equals arctan t sine t, t squared, and r2 of t is equal to t squared minus t, 2t minus 2 natural log of t. And we are told that they intersect at the origin. They may or may not tell you where they intersect. You may have to find that yourself as a separate part of the problem. But in this problem, they were nice, and they told us that these two curves intersect at the origin. So at 0, 0, 0. We want to find the degree measure between these two curves, which amounts to doing this. We're finding the degree measure between their tangent lines. So if you're ever asked to find the angle formed by two curves, you need to find their two tangent lines, or at least find the direction vectors for those two tangent lines, and you need to find the angle between those two direction vectors, the acute angle. Okay? So what are we going to need? We're definitely going to need some derivatives. So I'm going to take the derivative of r1. I'm just going to get started by taking those derivatives. I need an expression for r1 and r2 prime. Tangent vectors for each curve. This is a great section to review all of your derivatives as well. So make sure that you're looking at those rules from Calc 1 that I posted on Google Classroom to review your derivative rules. The derivative of arctan t would be 1 over 1 plus t squared. The derivative of sine is cosine, and the derivative of 2t, or of t squared, would be 2t. Looking at the second curve, the derivative of r2, first component, the derivative of t squared minus t would be 2t minus 1. The derivative of 2t minus 2 would be 2, and the derivative of natural log of t would be 1 over t. Okay. We need to figure out at what value of t these two curves intersect at, because I need to know what value of t to plug into my tangent vectors. So you kind of have to look and reflect a little bit here. In order to produce the point, it said the origin. So I need the point 0, 0, 0 to come out of this. So I have to think what value of t would make arctan be 0, would make sine t be 0, and would make t squared be 0. Well, that would be when t equals 0. It doesn't have to be the same value of t for the second curve. So let's check the second curve. What would make t squared minus t equal 0? What would make 2t minus 2 equal 0? And what would make natural log of t equal 0? That would be when t is equal to 1. So for R1, we're going to want to figure out the direction vector here, the tangent vector, evaluated at the point t equals 0. And for the second curve, we're going to want to evaluate this tangent vector at the point when t equals 1. So different values of t. Okay, they do not have to intersect at the same value of t. So for the first vector, what would I get there? I'd get 1, 1, 2. Pause. I would get 1, 1, 0. Sorry. 1, 1, 0. And for the second vector, I would get, plugging 1 in, I would get 1, 2, 1. Okay, so these are my direction vectors of my two curves of my two tangent lines. And they want the angle, the acute angle between those tangent lines. So this gives us a throwback to chapter 12. To find the acute angle, what I'm going to do, I know that cosine of theta is going to be equal to the dot product of those two vectors, r1 prime of 0 dotted with r2 prime at 1, divided by the product of the magnitudes of those two vectors. r1 prime of 0, magnitude of that vector, times the magnitude of r2 prime at 1. And if you're wondering where I'm getting this from, this is from section 12.3. We didn't do it with derivatives in that section, but we looked at general case of how do I find the angle between two vectors u and v. I take the dot product of u and v, and I divide by the product of their vector norms, magnitude of u times magnitude of v. In this case, u and v are just these two tangent vectors evaluated at 0 and 1 respectively. Okay. Okay, well, taking the dot product of the vectors up here, I get 1 times 1 plus 1 times 2 plus 0 times 1. So 1 plus 2 plus 0 over the magnitude of r1 prime would be the square root of 1 squared plus 1 squared plus 0 squared. So 1 plus 1 plus 0 times the square root of r2 prime at 1. 1 squared would be 1, 2 squared would be 4, and 1 squared would be 1. So we get 3 over rad 2 times rad 6. So 3 over rad 12. So what I've got to finish here, cosine theta, if you simplify 3 over rad 12, you get rad 3 over 2. So I guess you could use a calculator, but I would expect you to know the exact values from your unit circle in this problem. On the unit circle, they asked for the acute angle, so I know that I want quadrant 1. Where is cosine equal to rad 3 over 2? That would be at pi over 6. So they didn't specify radians or degrees, so I would accept either for this problem. Okay. It's a 30-degree angle, or pi over 6 radians is the angle between those two curves, between their tangent lines. Okay. Some other differentiation rules you should be expected to know in this case. Not surprising, a lot of these will look very similar to what you learned last year. Differentiation formulas for real valued functions have their counterparts for vector valued functions. So here's a theorem. Let's say that u and v are differentiable vector functions, c is a scalar, and f is a real valued function. Then the derivative of the sum of those two vector valued functions would be the sum of their derivatives, u prime plus v prime. Second rule, the derivative of a constant multiple times vector u would be the constant multiple times the derivative of u, okay? Just like it would be for a scalar function. Third rule says if we take the derivative of a scalar function times a vector valued function, we can apply the product rule like we learned in Calc 1. This would be the derivative of the scalar function f prime of t times the vector valued function u of t plus the scalar function times the derivative of the vector valued function u prime of t. So I'm just going to make a note here. This is a scalar function. So maybe it's like t squared. And u of t is a vector valued function. So that would have either 2 or 3 components, depending on whether you're working in R2 or R3. Okay, 4 and 5 are probably the ones you're going to have to study the most. You're taking the derivative of the dot product of two vector valued functions. In this case, this would be like the product rule you learned last year, except instead of just multiplying u prime times v, you have to take the dot product of u prime times v. So this would be u prime of t dotted with v of t plus u of t dotted with v prime of t. So this is not just normal multiplication. This is talking about the dot product. Okay. And because the dot product is commutative, the order doesn't matter. You could also do v dotted with u prime, and you could do v prime dotted with u. The order you do it in is up to you. However, for the cross product, if you take the derivative of the cross product, this would be u prime crossed with v plus u crossed with v prime. So it still looks like the product rule, except now these crosses are talking about the cross product. The one thing you do have to be careful with here is the order matters. So you can't do v crossed with u prime, and you can't do v prime crossed with u. You have to do u first, and you have to do v second because of the order that it was listed in. U was listed first, v was listed second. So for each of these cross products, something with u should be listed first, and something with v should be listed second. But besides that, these are just kind of like normal product rule that you would have done last year, okay? And then the last one's a chain rule. If you take the derivative of a vector valued function that's composed with a scalar function, you can take the derivative of the vector valued function, evaluate it at the scalar function, and then apply the chain rule. Then you have to multiply by the derivative of the function inside. Well, the function inside is the scalar function, so I'd have to multiply this entire vector by f prime of t. Okay. And these are just a couple notes about rule number 4 and rule number 5 that I mentioned. Okay. For the dot product, the order of the vectors doesn't matter. For the cross product, it does. So just be careful with that. Okay. A couple additional notes here. This is a theorem. If R is differentiable, and this is a key condition, if the magnitude of that function is constant for all t, so that function, that position function, has a constant magnitude that is not changing, then R prime, the tangent vector R prime, will be orthogonal, perpendicular, to R of t for all t. So in other words, your position vector and your derivative vector, your tangent vector, will always form a right angle so long as the magnitude of R is constant. Well, what is that another way of saying? That's saying R of t dotted with R prime of t will have to equal 0. That was our definition of two orthogonal vectors, right? Their dot product has to be 0. Okay, so this is a useful property. Visually, what it's saying is that if your curve lies on a sphere with a center at the origin, then the tangent vector R prime of t is always going to be perpendicular to the position vector R of t. Okay. And that would make sense, right? Because in this case, what was the other condition? You have to have constant magnitude. Well, this vector in green, you're in a sphere. The radius of the sphere is constant. So this would be my radius of the sphere. So that radius would be the magnitude of that position vector. And since we're in a sphere, this has to be constant. So visually, that's all it's saying, is that anytime you sketch the position vector in the sphere and you sketch the tangent vector to that sphere, they're going to have to form a right angle. If you're interested in the proof of this theorem, I'm not going to do it on the video. I'm going to say the proof is in your e-textbook. It's not a very long proof, but if you're interested in looking at why this works, you can take a look at your book. Okay? All right. For our last problem here, I would pause the video and I would try these problems out on your own first. And then once you're done, you can check your answers either using my key that I posted on Google Classroom, or you can keep listening in and I'll crank these out on the video at the end here. Okay, we've got two position functions. R1 is 2t, 3t squared, t cubed, and R2 is given by t to the fourth k. So I'm going to write this as 0, 0, t to the fourth. And the first one I'm going to write is 2t, 3t squared, t cubed. Okay. Part A. Calculate the derivative of the dot product of those two vectors by differentiating the product directly. So in other words, don't use the formula that we just learned on the last page. Let's actually find the dot product first, r1 of t dotted with r2 of t, and then we'll take the derivative of the resulting function. Okay. I mean, that's always an option you have if you don't want to use the formula. Sometimes it might be easier to just do this directly. So in this case, if we dot the two vectors from up top, we're going to get 2t times 0 plus 3t squared times 0 plus t cubed times t to the fourth. So we end up canceling out the first two terms and we get t to the seventh. Taking the derivative of that result, t to the seventh, I can use the power rule. I get 7t to the sixth. That was pretty quick. Probably can't get much quicker than that, but we'll try it the other way. If we use the formula using property 4 from the last page, if I take the derivative of the dot product using that, then I would get r1 of t dotted with r2 prime of t plus r2 of t dotted with r1 prime of t. Just using the product rule, the dot product version of the product rule. Okay. In this case, here we go down here. r1 of t was 2t, 3t squared, t cubed, dotted with r2 prime. r2 prime would be, if we take the derivative of r2, would be 0, 0, 4t cubed, plus r2 of t was 0, 0, t to the fourth, dotted with r1 prime. So we take the derivative of r1 would be 2, 6t, 3t squared. This is already turning out to be more work. Okay. So I'd probably, in this problem, if I was just asked to compute the derivative of the dot product, I think part A would be a lot easier, but let's finish what we started. Okay, applying the dot product here, what do we get? 2t times 0 would be 0. 3t squared times 0 would be 0. T cubed times 4t cubed would be 4t to the sixth. Plus 0 times 2 would be 0. 0 times 6t would be 0. And t to the fourth times 3t squared would be 3t to the sixth. All the zeros cancel out, and we're left with 4t to the sixth plus 3t to the sixth, which would be 7t to the sixth. Notice how cool is that? We get the same result. Not surprising. Okay, let's do this one more time with the cross product. I am going to write my functions up here again so I don't have to keep looking back. r1 is 2t, 3t squared, t cubed, and r2 is 0, 0. And for all of these, just to clarify, you could use IJK notation in your answer if you'd like for these vectors coming up. Okay, part C, we're calculating the derivative of the cross product of these two vector valued functions directly. So not using property 5 from the last page. Okay, so we're just going to take the cross product directly. That'll be step 1. So r1t crossed with r2 of t. I'm going to set up my 3 by 3 determinant, IJK. r1, 2t, 3t squared, t cubed. r2, 0, 0, t to the fourth. So I end up with I crossing off first row, first column. I'm left with the determinant of the little 2 by 2 that's made up of 3t squared, t cubed, 0, and t to the fourth. So maybe let me write this one out to be thorough. 3t squared, t cubed, 0, t to the fourth. Minus j, cross off first row, second column. I'm left with the determinant of 2t, t cubed, 0, t to the fourth. Plus k, I'm left with the determinant. If I cross off first row, third column, I'm left with the determinant of 2t, 3t squared, 0, 0. So now I get, let's see, I'm going to get I times 3t squared times t to the fourth would be 3t to the sixth minus 0 times t cubed would be 0. Minus j times 2t times t to the fourth would be 2t to the fifth. Minus 0 times t cubed would be 0, plus k times 2t times 0 would be 0, minus 0 times 3t squared would also be 0. So we have no z component at the end. So we end up with 3t to the 6th negative, don't forget the negative sign, 2t to the 5th, and then our third component is 0. And taking the derivative, so d dt of that vector, 3t, what was it, 3t to the 6th, negative 2t to the 5th, 0. Taking the derivative component by component would be 18t to the 5th, negative 10t to the 4th, 0. So that would be the derivative of the cross product done directly. A little bit more work than the dot product. Or, alternatively, we could use property 5, and we should get the same result. So let's finish by doing that. If I use property 5, then this would be the derivative of R1 crossed with R2. Remember, you have to keep the order consistent. R1 has to appear first. R2 has to appear second. This would be R1 of t crossed with R2 prime of t plus R1 prime of t crossed with R2 of t. Notice that I listed R1 first for both pieces in that formula. Only difference being the first time it was the position vector R1, the second time it was the tangent vector R1 prime. But R1 has to be listed first. So each of these is going to be its own 3x3 determinant, ijk. R1 was 2t, 3t squared, t cubed. R2 prime, we did in part B, I believe it was 0, 0, 4t cubed. Plus another determinant, ijk. The derivative, R1 prime, would be 2, 6t, 3t squared. And R2 was 0, 0, t to the 4th. I pause here and say already I can tell this is going to be more work because I have to do 2 determinants instead of 1. But they asked us to do it. So let's finish it. In this case, we're going to get I. This time I'm not going to write out all the 2x2s. You can pause and work this out with more time if you need it. Crossing off first row, first column, I'm going to be left with 12 t to the 5th minus 0 times t cubed to be minus 0. Plus j, cross off first row, second column, I'm going to get 8t to the 4th minus 0 times t cubed would be minus 0. I already noticed an error. This should be minus j. Sorry about that. Plus k times, cross off first row, third column. We're going to get 2t times 0 would be 0, minus 0 times 3t squared would be 0. Okay? Now we move on to the second one. Plus I times, cross off first row, first column of the second determinant, we get 6t times t to the 4th would be 6t to the 5th. Minus 0 times 3t squared would be minus 0. Minus j, cross off first row, second column, we get 2t to the 4th. Minus 0 times 3t squared would be minus 0. Plus k times, cross off first row, third column, 2 times 0 would be 0. Minus 6t times 0 would be 0. And so we end up with, let's do the first set in green and the second set we'll do in a different color. 12t to the 5th, negative 8t to the 4th, 0, plus, let's do the second one in blue. For our components of the second one, we're going to get 6t to the 5th, negative 2t to the 4th, 0. And now I can add component by component. So if I add the x components together, 12t to the 5th plus 6t to the 5th would be 18t to the 5th. And look at that. That matches the first component we got in part C. If we add the y components, negative 8t to the 4th minus 2t to the 4th would add up to negative 10t to the 4th. Let's compare. Look at that. We're 2 for 2. And the third one should be 0. And what do we get? Last but not least, 0 plus 0. Last time I checked, was 0. And so we get a perfect match with what we got in part C. I would say in this case it took longer. It won't always take longer, but there we go. So that confirms these properties work, at least for those specific vectors. And there's proofs you could prove these, but we're not going to do that. Okay? All right. That is taking derivatives of vector valued functions. In the next video, we will take a look at how to integrate vector valued functions. All right, good luck. If you have questions, please reach out.